So our next keynote talk is by Professor Cachin. Christian is a professor of computer science at the University of Bern in Switzerland, where he has been leading the cryptography and data security research group since 2019. Prior to that, he worked for IBM Research in Zurich during more than 20 years. He has held visiting positions at MIT, at EPFL, and has taught at several universities during his career in industrial research. He graduated with a PhD in computer science from ETH Zurich in 1997. He's an ACM fellow, an IEEE fellow, recipient of multiple outstanding awards, and he has served as the president of ISDR, International Association for Cryptographic Research. With a background in cryptography, he is interested in all aspects of security in distributed systems, and especially in cryptographic protocols such as consensus and blockchain technology. He has developed many cryptographic protocols, particularly for achieving consensus and distributed cryptography. And he has co-authored a textbook in distributed computing titled Introduction to Reliable and Secure Distributed Programming. While he was at IBM Research, he made essential contributions to the development of IBM Hyperledger Fabric, a blockchain platform that is known to this community. The talk the keynote talk is entitled Blockchain Consensus Protocols. With that, Christian, please.
Oh, thank you, Ari, for this long introduction. Also to Moti. Can you hear me? Okay.
Yes, we can hear you well. Please share your screen.
Then I will start sharing slides, and I also encourage you to interrupt me at any time, but you have to make yourselves audible because I am not going to see the chat nor much of the screens. Yeah.
Okay. So with that invitation from our keynote, I have enabled the unmute themselves for all the participants.
Yeah, that's great. That's great.
Yes.
And then you can mute them again when they walk out in some other place or something. That often happens, right? Okay, good. So welcome. Good evening, good morning. I'm going to talk about blockchain consensus protocols. And I'm so sorry not to be in Calgary, but that's the nature of modern conferences. We can be in one corner of the globe and in another corner of the globe next hour. I'm speaking from Switzerland today, where I've worked also, as Adi said. The world is distributed, and our protocols in blockchains are also distributed. That's one of their main features, I think. One of their main features is, now it's, what did I do? Something turned black. What happened here? Okay, I have to.
Yes, your screen is black on our side.
Screen turned black for some magic reason. Okay, then I have to start sharing again. I'm not sure what that was. Okay, let me just click share again. It could be that when I want to talk about sharing, about the distributed world, everything gets black. Yeah, this is what I wanted to show, okay? Distributed trust, what is it? Yeah, if you had your microphones on and we were in a room, I could ask you what it means. You would say something like, oh, we don't trust a single individual. We trust everyone a bit. Everybody has some influence over the consensus, and the majority is right. Why is it the majority? Well, it must be something that has to do with counting. Also, distributed trust is that we can tolerate nodes to fail, we can tolerate disruptions and so on. That's pretty much to where we go, and we want to make sure that this happens also with protocols. We want to implement this with protocols. That's the main task of what I'm talking about here today is consensus. More specifically, so-called Byzantine consensus from the founder of that part of our fields, which is Leslie Lampert, who also won a Turing Award, and not the least for formalizing so many technical problems in nice stories. And one of them is the story about the Byzantine generals. Now, a small preview already here before we go, and we're going to return to this later. Most of the time when we talk about distributed protocols like this, we mean threshold trust. We mean trust by numbers. We have a system of nodes. We have 7 here in that picture. They're arranged around the ring, but that doesn't really matter. It's important that they all know each other, and they have a assumption that they say, oh, majority is right. Actually, we need a 2/3 majority, in the sense that there's f of them that can be faulty, and strictly more than 2f of them, so there's strictly more than double the number of faults, are going to be correct. That brings you to the lower bound here, that there have to be and the number of nodes more than 3f. But these thresholds, they are there, but they are variations. They depend on what the fine print of your models are. But typically, this is what we mean. Yeah? We just count nodes. Yeah? So when we just count nodes, what does it mean? Let's go explore this a bit. Threshold trust. Yeah. Why is it n bigger than 3f? Has to do with safety and liveness, but not only. These are the things we want to achieve. Moti had this also on the slides. And I'm going to show you an example of storage, reading and writing to storage, which is the very simplest thing we can do here. And the other things, reliable broadcast, atomic broadcast, total order broadcast, or consensus, they come later. They build on this other abstraction here that I want to talk about first. But first, the playing field. Safety and liveness. What does it mean for protocols to be safe and live? If we have an audience of cryptographers here, and I've so far seen more familiar faces of cryptographers than distributed computing researchers, then you're focusing very much on safety. You're focusing almost only on the fact that on the property that nothing bad will ever happen in your protocol. And safety, that's a fundamental. So the protocol properties, the fundamental result by Alpen and Schneider, can characterize, so all the properties a protocol has to achieve, you can separate them into properties that are safety and other properties that are liveness. We haven't talked about privacy here, okay? But that may be another story. But if we talk about non-private protocols, you can separate all the properties into safety and liveness. Safety means nothing bad ever happens. Nothing bad has ever happened, because you can assert a safety property by looking back in time. If you don't do anything, it's always safe. Yeah. Liveness is the property that something good will eventually happen. This is a property sometimes overlooked by cryptographers, but safety bugs, liveness bugs can be much more difficult to find. Liveness bugs here, the protocol that violates liveness is much more tricky to discover, but doing something is always live as well. Eh? It's not necessarily safe, and only in the combination of the two properties lies what our protocols have to achieve, namely useful things. So only when you have safety and liveness, we're good. If we apply this to blockchain, it means safety means that we reach the same decisions, that they all agree on who owns which coins. This is very important, because otherwise they would never have become taken on any kind of value. It could also mean that the ledger doesn't split the views, yeah, in the jargon, that these ledgers don't fork. That's safety. Now, liveness is also important because it means that the protocol does something useful, namely that it doesn't need manual intervention, that much more importantly also in the economic perspective, that the protocol maintains its market liquidity, so that people who want to sell coins or want to buy coins when the market is in a turmoil, that they can actually do this. This type of liveness problems has recently led, when you observed how the algorithmic stablecoin swap, the algorithmic stablecoin crashed, they have been seen there again in the past. Yeah. So we have to also make sure that the protocol makes progress. With that said, let's now turn to some example. And this is it's going to be a very simple example. And as Adi said before, There is a textbook about this that I can really recommend. It goes from the simple example here all the way to consensus. It was done though just before blockchain, right? So what we want to do here is talk about the simplest of all these concurrent abstractions, or let's say concurrently accessed abstractions, where you can think this is some storage location that is in a computer system that is accessed by multiple processes concurrently. Already there, you have the issue to say, what is the semantics and what is the liveness property if we're all trying to access this at the same moment in time? Like if many processes do this at the same moment. That's exactly why there is language for this. And there's a simplification that has turned this storage location in a so-called register that only supports two operations listed up here, which are write and read. And they all have, let's say, a moment in time when they start. It's like an event, an invocation event that you can think is for my implementation or for my abstraction, an input event when a process, a client says, hey, I'm going to write some value into this, and I need a confirmation when it has happened. So this is an operation that will return. It will just return, okay, I've written. Same for reading. When I want to read what's there, I'm going to ask, oh, give me what's written there, and I'm going to get some value back, hopefully. You can now think, I started to say that these are actually memory locations in a multi-threaded computer, but you should really think of them as locations on a ledger somewhere, or locations or storage locations in some cloud that you don't exactly know how it's implemented, but it's implemented by many computers at the same time, such that it won't fail. There's one more simplification I want to make here, namely that only two processes have special roles here. There's only one, a writer, that can write, and there's only one, like R, who can read from this. This is going to be, in this jargon again, a single reader, single writer register, where we have specially divided roles like this. Now we can start to define what it means to access this storage location, this register, concurrently. And there's just two, right? Just these two processes. And now here's a picture, not yet the picture that will come, but here's just what I said, that we have this abstraction, and we want to implement this in a completely asynchronous way. No common clocks, and we don't know how long messages are taking between nodes. A word on these assumptions that is also relevant in the blockchain context. Whenever we make an assumption, it's a vulnerability of our system. And everybody who works in security knows this. You make some certain assumptions, then you argue that your system is secure under these assumptions. But if somebody violates the assumption, things outside of the model or outside of the box, well, then your system is usually going to break. So the fewer assumptions, the better, the more resilient your system becomes. So if you are not assuming anything about time, like that your message that you're sending to the network reaches every participant within an hour, if you're not assuming something like this, your system is more resilient. I mean, I was making the example with an hour because Bitcoin, for example, if we don't reach all the miners in the system within an hour or so, the system will just fork, yeah? It will split, will violate safety. Now, one more notion here, we can say that an operation precedes another operation when this ending event of the first operation of the O appears before, happens before the invocation of another event, like when you start another operation. So when an operation ends in some magically, hypothetically viewable real global time that may exist for a global observer, but not for us, when this first operation finishes before the second operation is invoked at some other participant. And if they are not sequential, in the sense that one precedes the other, then they are concurrent. So how should our register now behave when it is accessed concurrently? Yeah? And so here we have this writer. We can actually have two readers here, yeah. But we have here one writer, and he has written some value x in the first operation, and he's going to write some other value y in the second blue operation. And here is here are two readers, and I think we should just focus on the second reader here, who, for magic reasons that are conceivable because the two operations overlap in the time domain that I'm highlighting here in the black, the reader 2 has already picked up the value that is written here, and it's possible, right? Now it's possible that also the orange reader 1 in this operation here picks up this value, but it could be the case that red reader 2 just runs another operation here. I mean, you could think of a third or fourth process here, but it doesn't really matter. When this other process, when the second read operation of the reader 2 occurs, now we're wondering what it should return. Yeah, and there's some terminology here, and I only want to argue or to talk to you about regularity, which is a property that means that in this case, it's fine to return either the value that is being written here in a concurrent, yeah, because you see an overlap between these two operations, in a concurrent write operation that is concurrent to this second read, or it's going to return the value that was written there before in the most recently completed write operation that has been already finished in the past, right? So in this case here, reader 2 might read X or Y, and this is fine. And this is actually sometimes also good because we don't want to pay the cost for a stronger semantic. Now may be a good time for somebody to ask a question if you dare to. Otherwise, I'm going to continue, or maybe a question comes up. You want something, of course, that we could call atomic or linearizable when you realize that one has already read the new value here and returned it earlier than this operation. So in some magic hypothetical execution, the register's content has already switched from X to Y, so the read operation must also return Y. And this is indeed much more likely what blockchains provide, but in order to illustrate what happens here at the low level, the first, the regular, I should say, the regular semantics applies. Yeah. Okay, so there's a few more executions here, but let me just highlight here how we can implement this very simply. We're going to use our n bigger than 3f nodes, replicas. F of them are Byzantine, so they may do whatever we want. And they also store, they are the ones who store our values. And they can sign. I mean, the client, the writer has a signature, has a digital signature where you can say, hey, I'm writing a certain value with a logical timestamp. Because you've seen, we're writing to this storage location over and over, many times, yeah? And it's this what serves our coordination. So because, and the writer now controls what are the so-called newer values by maintaining a logical timestamp. And for each write operation, you will first increment this timestamp and then issue a digital signature on this timestamp and the new value that it wants to write, and then send this triple of timestamp, new value, and the signature to all the replicas. And then it's going to wait for a so-called Byzantine quorum to acknowledge that they're going to store it. Yeah. If you're just thinking in terms of 3f plus 1 nodes, this so-called Byzantine quorum, this quantity here is 2f plus 1 nodes, yeah, or same as n minus f, because 3f plus 1 is n. So we have a group of that size that has acknowledged. Why? How do we see liveness here? The liveness property is ensured by this because the writer wants to terminate this. The correct replicas are going to return an acknowledgement that says, hey, yes, I'm storing this value. And since only f of them won't respond, they're Byzantine, and the n minus f is bigger than this number here, that's why this protocol here is live. Same for the reader. The reader will actually also ask all the replicas for their current values, for these tuples or triples that they're storing. and then get something back, and it also waits for a Byzantine quorum of those responses. I haven't argued about safety yet, okay? Safety will come from the fact that the reader is going to look at the timestamp that is in there, at the logical timestamp, also at the signature. It's going to validate the signature. If something comes from a faulty node that comes with a supposed forged signature that was not from the writer, it's going to filter it out. Otherwise, it takes the value with the highest timestamp, yeah? And so I would like to illustrate this. First, a little bit of pseudocode that is basically straight from the book, but you don't have to read this, but we'll return to this later. But here's a picture. We have again our writer here starting and finishing the operation. It's going to send out messages, and it's clear the messages take time. So this message here that I'm showing is going to arrive at process Q, which is one of our 4 replicas in this minimal system here, way after reader here wants to read its wants to execute its operation. So reader may not hear. Reader does the same, right? Reader also sends messages out. Send me your values. And here's from this node here, which is a node that is correct and has been storing the most recently written value. It's going to hear from this node here that has not stored yet the most recently written value because it only learns about it over here. Yeah, these nodes are distributed. And then it's going to get an answer from the faulty node here, which is the corrupted node that sends whatever it wants. It could send a tuple from an older write operation with an older timestamp. And from this, the reader can infer what is either the value being written concurrently or the value that has been written there most recently. So this is an execution that could happen like this in the system. And it shows you also why we need the n bigger than 3f property. So we need 4 nodes to tolerate 1 corrupted node, because we cannot rely on the answers from the corrupted nodes like this one here. And then among the remaining answers we are receiving, which is just the first 2, we need somebody who was involved, who's up to date. But at least one of them again, or at most one of them again, could be slow because it's not been involved most recently. So that's why we need to discount the corrupted ones and the slow ones, and then we're gonna have at least one that is correct here in this overlap. And as I said earlier, depending on the family of protocol of assumptions, there are different types of those quorums here in place. Yeah. Any question about this time? So let's look at a little bit of code, how this looks like here. This is again the code that would express this in textbook style. So here we are waiting for those responses, for those ACK messages from the Byzantine quorum. And when the reader comes, this is the second here, it also waits for these messages from the replicas for this many, okay? That's it, yeah? So I think we've already argued why this maintains regularity. I want to now proceed to talk about the types of protocols that all use this model. I mean, Libra, Facebook's DM, Novis, coin system use this model. This is perhaps one of the most prominent one. Hyperledger Fabric blockchain may or may not use it because it doesn't really turn on the Byzantine fault tolerance by default. There are countless other chains out there in the high market cap that use some variations of these protocols. Other protocols are using different mechanisms. That's also true. But this is the foundation of those protocols for blockchains that achieve consensus finality. Yeah? They typically make also this assumption about a number of nodes or an amount of stake that can be tolerated to misbehave. That is this line here of weighted stake. Like if we add weights to the votes, we can vote with stakes that we hold in the protocol. Yeah. These are jargon for the protocols we can implement and the blockchains. Yeah, this is basically a replicated state machine that goes back as an abstraction to the 80s that has been formalized here as the crucial way to maintain consistency in the distributed system. Let me now continue here to review the assumptions we made here. Yeah. And it's about symmetric and threshold trust. So the threshold trust that we just used is symmetric, right? It's also egalitarian, right? Because everybody, I mean, unless we are using the weights, we are not using the weighted votes here because every is more democratic. Every member has one vote, yeah? So all the nodes are equally trusted. They all have the same influence. But importantly, also all nodes trust in the same way. All nodes adopt this trust assumption. You couldn't just join the system and say, hey, I'm much more trustworthy. I'm going to think that at most one of them can fail because I believe much more in my colleagues here. Protocols are not formulated in this way in these models typically, yeah. And in security, it's for simplicity, but it's also there are mathematical reasons for this behind. Now, this is symmetric, right? If we could define something that was not symmetric, we could allow certain nodes to have much more influence in this. And this is indeed what has happened, at least in distributed computing, but also somewhat in crypto research, through these introduction of so-called quorum systems or generalized Byzantine quorum systems that I'm not going to go through the whole mathematical formulation here, but Malki and Ryder introduced those in the 90s, where I would say we have an arbitrary specification here of who could fail, right? And we say on the picture on the right here, among X, Y, and Z, any two could fail concurrently, jointly. Yeah? They could collude against the rest. And among P, Q, and R, also two of them could collude against the rest. But actually, X and P here, they're sort of not colluding against the rest. So you can see that the property we had before, namely that n had to be bigger than 3f, right? This is not maintained. Well, we can't say this here because some of the faulty sets here contain two nodes. I mean, any two of these up here could fail, or any two down here could fail, but not one of the upper sets and the lower sets, right? Jointly. So in that sense, because when you study this further, this protocol also allows us to run exactly the same protocols, but not all the nodes are equally trusted anymore. It's no longer trust by the numbers. We have a different characterization of what it means that they could fail. We can express a much richer structure of trust assumptions with this, yeah? Any remarks or ideas about that? Let me just continue by saying that it maintains the fact that all nodes trust the others equally. So all nodes adopt this assumption to be participating in that system. We don't see that system in the wild yet. We see variations that are simple to specify. But this is actually being looked at, okay? Here's a mathematical definition. We don't want to go into this formalization here, but we're going to go a step further and ask the question, what happens if I don't have this a priori agreement with everybody else on who I should trust how much? And this leads us to the asymmetric trust. This leads us to formalize and formulate what it means that some nodes can trust in their own way, that basically every node can pick their friends and trust them. And that, as you see, as you already realize, opens up to a much broader spectrum of fault assumptions that you can have. Let me start with this here also. That's another motivation. Not too sure how to pronounce it. The gustibus non est disputandum in Latin means you cannot argue about taste. Yeah, either you like this dish or you don't like this dish. You cannot argue about taste. And that's essentially the same for our security assumptions. I'm convinced that many disputes in computer security arise that are not actually disputes because some people like their security assumptions just much better than they like other security assumptions. And then they start to argue about the model and about the security assumptions rather than the construction where it is safe under certain assumptions. Yeah, and they can go on forever arguing about it because it's just like saying whether you like better tea or coffee, or you like better this or that variety of chocolate. Let us go into the technical detail and ask, could we also say that P now formulates a model, how it says, oh, I could think that my neighbors here, because they're still sitting around the ring. Yeah? You look at the picture here, they're sitting around this ring. My neighbor here, Q and R, which are my immediate neighbors, they may fail alone, but they're not going to collude against me with others. Yeah. But those who are further away, those out there, maybe two of them could even collude against me and fail in that sense, but not all of them, not all three of them. Yeah. So that would be a asymmetric trust structure that is actually at the heart of what I'm going to talk about next. And that is something that has been initially studied a bit in academia, but much more also in the blockchain world. And if you look about this now, and I mean, this is just the view of P. This is the worldview of P. And everyone around that ring could adopt the same rotated trust assumption. And then you would see that they all trust in a different way the other members of the ring. This comes from blockchain systems. This was initially introduced in a certain way by Ripple. Ripple is one of the oldest chains of those systems. Ripple started when some people wanted to model the original inventors of Ripple wanted to model the openness of Bitcoin, where everybody can participate, but implement it with a quorum type protocol. So there is a white paper from 2014, and the most important, and it's been one of the top 10 list coins for a long time. And its main feature is that if you're participating in that system as a validator, you're declaring a so-called unique node list, or you're adopting a unique node list that are the nodes that you know. It's like your neighbors. And you have to trust a certain number of them, a certain fraction of them. And the protocol intends to achieve a Byzantine fault-tolerant consensus based on this assumption alone. Yeah, and so here are some older copies from their documentation, right? So the trusted validators is the nodes that you know that are trusted not to collude in an attempt to defraud the server like yourself who is receiving their answers. These answers are basically votes in the protocol. What does it mean to have this subjective trust? Yeah, I have my list of friends or neighbors, and you have your list of friends or neighbors that you trust. There should be some overlap among these lists, otherwise we can't reach consensus, right? And that's indeed the question that is behind that system, or behind the security proof for that system, if it exists. Yeah. Here is a picture from the original white paper where it is derived that this list of one node, so and the list of the second node must intersect in a number of nodes that is only 20% or more of the size of one of these lists, of the bigger of these lists, which is very little actually, yeah, and which turned out to be not the right answer, right? So this overlap of 20% was quickly seen to be not sufficient in a paper in 2015 here, where they argued it has to be at least 40%. And in 2018, the overlap was also already recognized to have to be almost 100%. And these are authors from Ripple, by the way, at the time. And we had a paper last year, 2 years ago, where we showed that even if the overlap is 1, it's not live, or even if the overlap is almost 1, it's not safe. Yeah, we don't have the time to run through these examples, but basically you can construct executions that may occur under certain assumptions or on the network that will make them in that way here either adopt a ledger L or others adopt a ledger L prime, and thereby violating safety. Yeah? And here you see how the two groups of nodes are not exactly the same. Yeah, I trust the vertically striped one, and the other ones trust the horizontally striped one. And also for safe, but for liveness, it's even enough if there are some Byzantine nodes that send conflicting proposals to others. Yeah, that would not have been necessary in a certain way, because we do have consensus protocols that work on the assumption that they all trust the same, but this is not the assumption that was used here. Yeah? What also happened at the time when we announced this was that we saw absolutely no effect from this, yeah, because at the time here in early December, the blue star occurs, nothing happened, but the regulators then later, like a couple of weeks later, sued some founders of Ripple, and that actually led to the price of the token crashing a bit, right? I think it's today higher than it was there. So you see that sometimes the scientific analysis behind protocols do not really have a large effect on the perception of such coins. On the other hand, one has to say that the system is not operated in a way that is really containing malicious insiders, because today all the nodes in that system, they're downloading a validator list from the centralized Ripple company that comes with a signature by Ripple Labs or something. And that's the list that they trust. They are not really free to trust their own thing because it might fork. And so this list has, well, at least the list has fewer nodes that are owned by Ripple nowadays. Yeah. So this is one of the types of protocols that went into its own trust assumption into asymmetric trust assumptions. Yeah. There is another one that has a relation to Ripple, which is Stellar, because it evolved as a fork originally of Ripple. It evolved from ego clash of founders, but that's over in the sense that they then started to build their own protocol. Yeah? Because in early in its operation, they used the Ripple code base, and it's not sure what happened then, but the consensus failed, the ledger forked, they had to be restarted. And then they had a computer scientist formulate another protocol that is called Federated Byzantine Agreement, where they put these ideas on a somewhat more scientific basis compared to the Ripple white paper. What also happens here is, I'm not going to talk in all these details here, but what this protocol formalizes is the notion of a quorum that doesn't look like the quorums we have before, but every node in the system can now declare a set of others that are convincing for itself. This is a slice. Yeah? They call this a slice. A slice, for me, is a set of other nodes that if they tell me something, I'm going to agree with them and adopt what they say. Yeah? It goes without saying in some way that the slice includes myself. I never think that I'm failing for myself. And then if you have a set of nodes such that for each of its members, there is such a slice, they call this a quorum. Yeah? However, these quorum slices here don't really have a clear-cut relation to the quorums we studied before. So these quorums here are not properly, in my understanding, related to the quorums that we have otherwise in the literature. And in fact, this is subject of ongoing research to clarify their relation. Nevertheless, the system allows to some extent what also Ripple does, namely that you can declare your own trust in a way. This is a picture of how the example config file looks like. You have tiers here, you have a top tier, and you have like 5 nodes, and you're going to use at least 2/3 of those 5 nodes, whereas these 2 nodes here on the right, they're so-called virtual nodes that are provided again by a subgroup of other nodes. Yeah? So you're going to say, oh, I need at least 66%, which is probably 2/3 of the top group. And then from this group here, I need 2 out of 3. From this group, I need 3 out of 3. And among the 3 out of 3, there is again a virtual node that is provided by some less trustworthy nodes. And I just need half of them, right? So this is something we can explore and think about. And what's even more interesting, that everybody can pick their own set like this. So I'm not going to go into the details here, but this is how it's implemented. One can analyze the centralization structure of this system as well. This is a paper that was also in a security conference a few years ago, showing a certain centralization here among the red nodes, yeah, that are operated by the Stellar Foundation. And what happened a little after the publication of this result is that probably the system was reconfigured a bit, but it halted at least once, had to be restarted manually. It also halted again just a year ago. And the systems will do this, right? Because if there are not enough nodes around that are live, the systems will just, those systems here are programmed to violate liveness, as opposed to the Bitcoin type systems with Nakamoto's protocol that are going to violate safety by just forking. Yeah? So here are some stories about these networks that went offline. We don't really have to study these. And we also don't really want to study the relations mathematically, but just to wrap up, it's not clear for me whether this is actually a consensus protocol, because the relation to the existing protocols here today still remains open. Nevertheless, it has not stopped the system from being prominent and from being used, and its token having a high valuation. Yeah. Okay, that's the motivation still for going into so-called asymmetric quorum systems, but that's not going to be much more now, because those asymmetric quorum systems are the formalization of what we have seen before, of those Byzantine quorum systems, extended such that each participant now can declare one such quorum system for itself, like the ring we had seen. Let's not focus too much on this. Like the ring we had seen here. So P can declare a trust assumption on its own of this kind for the others. And every node among the 6 here could declare such a trust assumption. And when we do this, then we have an asymmetric quorum system that actually is able to reach consensus, to make progress in protocols that are straightforward extensions of the existing protocols. That's also roughly where I'm going to end. So we're on the finishing line soon. I'm not going to mention the mathematical properties, but we can prove that such quorum systems exist if and only if there is this property true, that this property holds, which is again a generalization of properties that we understand for the symmetric case, and which is a strict generalization of the condition that n must be bigger than 3f. Yeah. So we have an analogous mathematical structure here. Because there's one more thing. When we run the protocol, we're going to have different types of nodes now from before. Before, we had nodes that were actually faulty during the protocol. These are the faulty nodes in some set f. And all the others are correct, right? In this model here, we're also going to have some naive nodes who picked the wrong friends. These are the nodes that show up only in this picture, in this model here. These are the ones that are correct, but they have made too strong assumptions. Yeah? And so we cannot actually guarantee much for the naive nodes. We can only guarantee something for the wise nodes. And these are the ones that have made the right choices. And if there is a set of such wise nodes that also contains a quorum for each member node, then we have a guild. And the guild is could be seen roughly as an analogous to this quorum in the stellar formalization. But as I said, the mathematical details are not ironed out. So when we have such a guild, there's a set of wise nodes, then they have a protocol together. They can do consensus because they have the right assumptions. Such protocols can be seen as strict generalizations of the existing protocols. And I'm showing you here again the code from the register that we had looked at half an hour ago. So here we have this line where we said we need to hear from more than n plus f over 2 other processes. And in the asymmetric formulation of this protocol, we're just going to replace this blue condition here that I have to read by the red condition. That means I have to hear from all the processes that are a quorum for me. Yeah, and this guy here also has to hear from all the processes that are a quorum for him or her, such that they can continue the operation. So that allows flexible trust among between the reader and the writer, and the rest of the protocol remains exactly the same. That means also here we have a couple of these protocols developed over the last 2-3 years, all the way to Byzantine consensus, and their relation compared to the textbook and compared to the standard literature that is like 40 years, goes 40 years back, is very well understood. And that brings me now to the conclusion, actually, where I wanted to repeat that trust is not only in the numbers. Trust can be more general. That would be the general's trust, generalized trust. Trust can also be asymmetric. It's not necessarily the case that everybody has to take up the exact same trust assumption. However, you cannot have totally disjoint trust sets, because then it's obvious from first principles that you cannot have consensus. So there's some coordination necessary. Determining how much coordination this is, the degree of overlapping trust you need to have such a system, that is still open. Yeah. And here I'm listing some URLs. Basically, when you go to the crypto at Unibern, you'll find this. And I'm listing also some literature references that I'm going to leave up, so you can have a look at those as well, to read up on the mathematical details of what I mentioned. And that brings me to the end. Thank you.
Thank you very much, Christian. Amazing keynote talk. Everyone join me in thanking Christian for this amazing talk. Christian, I have 3 questions. You invited people to unmute themselves and ask the question, but everyone was awfully quiet. So I'll ask my first question and invite everybody to either use the chat or unmute themselves and ask their question. So you mentioned that the book that you wrote, Introduction to Reliable and Secure Distributed Programming, was written before your work on blockchain. And it was, I looked it up, it was published in 2014. That's around the time that where most people heard about distributed computing. It's 2013 that Silk Road was shut down by FBI, and that's where most people heard about Bitcoin anyway. And so my question is this: if you had a crystal ball and would have known about all the ups and downs of what we call blockchain now, or distributed computing now, how would the book Introduction to Reliable and Secure Distributed Programming be different? What would you have added? What would be some of the assumptions that you would have clarified?
Okay, it's a good question. I mean, certainly, I mean, this book existed in a first edition that did not have Byzantine protocols before I joined as an author even. So I joined only for a second edition here. And the first edition was 2005-06, yeah.
Even
in
before Bitcoin.
12 or so, we would not have understood the Bitcoin protocol in the same way that we understand it today, because it was a heuristically proposed protocol. There have been several academics who mentioned that the paper would have never been accepted at one of their conferences. Yeah, because the proof had to be in eating it then. The proof had to be in making it actually show and demonstrate its viability. I mean, the Bitcoin protocol I mean here now, and that one that is based on mining. That was only understood 5-6 years later. So nowadays, yes, we would also explore in future revisions of this literature, we will also explore the rich and very rich landscape of such protocols that has come up from has been developed from about 2016 onwards. Yeah, many of them are a bit, how should I say, like the early days of cryptography, there were a lot of snake oil vendors. I mean, there were a lot of people who brought their own cryptography that were characterized by Bruce Schneier. Some have heard of him as an influential voice in the space as snake oil crypto vendors who didn't know what they're doing. And there are some of those protocols also here. And it's our job to make sure that we understand them better. It's not the case that we already do understand all of them. And it's what you also have seen, it's not a prerequisite to getting your token launched to have a sound security proof.
Absolutely. We'll look forward to the next versions of the book. Definitely, as a textbook would be a great read for our students. We have 3 questions on the chat. I'm going to read them one by one. A question from Ray: would asymmetric quorum systems skip proof of work? Is there a notion being permissionless?
Oh, yeah. The answer is clearly yes. Asymmetric quorums are not based on mining, are not based on this type of power, are simply based on assumptions you make about other nodes. Why you are assuming some nodes are more trustworthy than others remains open. Yeah? But it's a strict generalization of the existing voting-based protocols. This should relate to some notion of knowledge about others, who you know in the system. Yeah.
Awesome. The next one is from Vicky. With so many complex asymmetric trust assumptions, what is the best strategy for making standardized cross-protocol comparisons of trust?
Well, I think you can't really compare the trust assumptions because they are like the taste. Yeah, we either like this dish or we don't like that dish. But we can compare them along their scientific soundness, and that's what we can do. Often in computer security, you can only empirically validate security assumptions. You can see that this and this assumption is getting broken all the time now, so we have to make a stronger one. And that might also happen here. It's not clear. Those protocols, or those formalizations haven't been developed far enough in order to deploy the systems. And Ripple and Stellar both are in operation, have been in operation for a while. They make some very simplifying assumptions compared to what actually could go on here. Yeah, especially since it's not clear that if there would be some malicious insiders, how resilient to those they would actually be. Those are the protocols.
Thank you. The next question is from Jeremy. Have you looked at the consensus mechanisms in Avalanche? They call it meta-stable.
That's a very good question, right?
What are the pros and cons?
This is a very good question. Yeah, you should expect some blog post or archive report, let's say, in the next couple of weeks on that. Yes, it is certainly not the case that the original Avalanche white paper had been peer-reviewed and published in a peer-reviewed venue. This is not the case to my knowledge. It's also, and as everybody can observe when you read the Avalanche white paper, it's not the case that those simple protocols that come with a little proof in there, or with a proof that I trust, these protocols are not used under their assumptions in the second half of the paper. So there is a little disconnect between 2 parts of the system, which we can talk about at another venue some other day. But this is a very interesting protocol as well, because it doesn't, it seems to rely on some kind of symmetry breaking mechanism. The important thing there is that in order to become a validator in the core group, you have to make a down payment and investment in 5 or 6 digit figures, dollar equivalents, I would say. So, and you're going to lose this if you misbehave. So it's not so easy to actually show, it's not so cheap to show a violation in those protocols. Yeah.
Mm-hmm. I see no other questions on the chat and no one has unmuted. So I take advantage and ask my next question. So you cover several famous blockchains. Ripple and Stellar. Mm-hmm. Based on what we know and what we don't know about Diem, or what used to be called Libra, what are your predictions about it? from the perspective of how it's going to revolutionize or at all change the
Diem
system?
and Libra, well, Facebook gave up on it, right? They're gone. Facebook has sold off all the assets. The protocol is open sourced. There is now so Facebook has given up on it, and I think they met all the regulators' concerns, except for the fact that was more the politicians, the political concern that there was Facebook behind.
Mm-hmm.
So
was that a strategic move, do you think, that for
yeah.
the betterment of the actual protocols, Facebook is now, or Meta has washed its hands now? So
no, I think the protocol itself would have worked. Yeah, the system would have worked, but it's just that the business side and the clashed with the politics, and they gave up. Except that now there's some of the core people have formed or joined another company called Aptos Labs, and you can look for that. They're trying to get it started again. Yeah, they don't have the backing of Facebook. Yeah.
Do you think they can revive it?
They will certainly revive it in some form. There's a testnet running now. It's not clear what their coin is going to be or how much it's going to be worth, because remember, the coin would have been a stable coin of some kind, and stable coins have received in the last month especially, again, a lot of attention. Yeah, let me just say it like this.
Okay, great. So we have another question from Quinn. Thoughts on other kinds of timing attacks, specifically attacks like MEV, that use automated bots to front-run transactions. Can these broader attack vectors be modeled using Byzantine assumptions alone?
Yeah, definitely. I think they should. You can only model those using counting how many nodes have received something before another thing. So there is work along these lines in the sense of preventing this. I invite you to go to the blog here and read one of the top posts, which is about order fair consensus. There's a paper that we've recently presented at Financial Crypto, which is the conference that Moti mentioned earlier, which took place again, or which takes place again, since the pandemic faded a bit in the Caribbean. Yeah?
I have one last question, and I'm also buying everyone time if there's also questions from the audience. I really love that saying about you cannot argue about taste. This is like, I'm going to use it. And security models and the disputes about them, cryptographers are used to this. Like, it's, as you said, people are fixated on that and don't move to actually the constructions or the rest of the contribution. So as cryptographers, as you said, we often try to achieve an ideal, which we may not agree on because of the taste, but also it may not be realistic in the real world or the context that we're working on. So this is probably a bit far away from the actual topic of your talk, so I apologize in advance for that. But I wonder what your opinion is about this. Oftentimes in the friction between usability, efficiency versus security, security loses in the real world, right? Or security is an afterthought, for instance, by IoT manufacturers, because they are trying to focus on the efficiency and user friendliness and this and that. So what are your thoughts on what we can do to improve the situation so the security assumptions that you talked about are not going to result in an all or nothing security reality for the end users?
Well, let me say, security is very often an afterthought, and security very often makes systems a bit more expensive. Always, you don't see a security as an observable property. It's only a property that you can falsify, like by demonstrating an attack. And that's when people come. Huh? Cryptographers are not the best people to pick your security models, because cryptographers, or the security assumptions, because cryptographers always worry about yet another attack, yet another violation of privacy. For this, we have to turn to the bigger world, and we have to turn to everybody's understanding. We may also have to turn to the attackers, yeah? The attackers who are starting to sniff networks or attack this or that just because it's cheap and because they can, and then it will be done. To give you but then when we develop as cryptographers or developers of protocols or so, when we develop new systems that protect things better than past systems, we're almost never wrong. Because if a system is also relevant, this is a big if, yeah, not all systems are relevant. But if a system is relevant, people will come with the attacks and they will want to buy this extra security because others talk about the insecurity of the deployed solutions. Let me mention garage door openers, key fobs, these keys that you carry in your pockets, that you approach your car, you get close to the car, and then suddenly magically it opens, right? The distance bounding attacks. It was academic research, and people thought ahead, oh, this is actually a problem. They demonstrated security problems, and then they showed how to fix them. Also, people implemented broke the type of crappy crypto. Some of those had really built in from the start when they used they didn't care. They founded their startups. These startups got bought up by the automobile industry or by the suppliers to the automobile industry. This is how you grow industry. Similar things happen to multi-party computation, cryptographic protocols, to zero-knowledge proofs that were sort of crazy academic ideas in the 1980s or 90s, which are startups nowadays. Yeah. And so this is the way I think that technology and history will go. It's not the case that every technology will be used like this, but when there is a perceived need to deploy it, that you can convey to many people, then it is going to be used.
Great, thank you very much. Really appreciate your valuable insights. So I'm going to take it back and think about the next thing I want to consider in my work and at my lab. So everyone, please join me in thanking Christian. This is going to wrap up our first session.